All right, I think it's time to get started. My name is Wright. I'm going to talk to you today about an open source project called Quine. The topic of today's talk is about streaming graphs because we can't afford to query anymore. So one thing you should know about me, my background and history here is really coming from the data platform world. So high volume data moving very quickly. The question has always been, what does that data mean while it's moving? So in flight, in transit, what does it mean? And probably like a lot of people here, 10 years ago, I tried to convince a whole lot of data platform folks that graphs are amazing and you should put them in your data pipeline because you can pull a lot of information together and understand what's happening and get a lot of value out of it from that perspective. But these folks come back around and always kind of indicate that, sorry, graphs are just too slow. We can't put them in a data pipeline. Sure, they're powerful, they're cool, they're great, but they're too slow. And in truth, graph databases are too slow for high volume data pipelines. And graphs are not databases. So graphs put all the pieces together, they focus on the relationships, they give us the ability to query at a high level language, let us run graph algorithms and do graph processing over that data. But the database part has a different job: to store it, to keep it persistent and durable on disk, to be resilient in the face of hard disk failure and machine failure. Because really what we want from that database part of the problem is the ability to combine really old data with what is happening now in the stream while data is flowing and moving really fast. So that distinction between graph databases being slow, graphs could be fast, even if graph databases are slow, led about 8 years ago to the creation of this open source project called Quine. Quine is now maintained by the team at our company called ThatDot. We were very grateful to have support from DARPA in the early years of creating this technology. And it is now 8 years in development, and we just open sourced it last year. So Quine is the topic of conversation for today. I'd love to tell you about what it is, how it works, how to use it, and some of the key capabilities that it really unlocks for streaming graphs in the modern world. So this question, what is Quine? In short, Quine is a streaming graph. It is like a graph database. It's meant to give you that graph processing capability, that graph storage capability, but to put it in a data pipeline, which usually means plugging into Kafka on one side and probably Kafka on the other side. So data streams in from one end, builds the graph, and then graph results come out and stream into the next tool. So that's kind of the high level picture of Quine. And instead of calling it a graph database, we focus on like what it can do. High volume data coming in, that data might be logs or alerts or metrics or JSON data, protobuf data, whatever format it's in. High volume data comes in, the graph does its internal work to turn it into high value data going out. If we're doing it right, it's a smaller amount of data going out because we've processed it, we've understood it, interpreted it, and now are sending it on to the next system. So using Quine is really this two-step process. First, define a high-level graph query that is an ingest query. Take a stream of data, use a graph query to build that data into a graph structure. And then second is use something that we call standing queries to monitor the graph. So this is a query issued in the Cypher language, just like normal, where you'd issue a graph query, but it stays live and active, pushes itself through the graph. Every time the graph changes so that there's a new result, the results of that stream out to the next system. So that's kind of Quine in a nutshell here. I don't know what happened to this slide. There we go. It is meant to integrate with all sorts of existing tools and technologies. So if you're using Kafka or Kinesis, or you've got server-sent events or data coming in through a REST API, WebSockets, files, standard in, all sorts of different things can be the input for data coming into the graph. So as data streams in, we use an ingest query to build the graph. Quine communicates with an actual database, the data storage layer, something we call a persister, to actually store the data, make it durable, resilient, pull it back in to do the graph computation as needed. And then when results are found, those stream out again, to a lot of the same technologies, out to Kafka, Kinesis, SNS, SQS, lots of different options here. But also, results can call back into the graph. So this starts to get a little mind-bending and insanely powerful to say, watch the graph for a certain complex pattern. Every time we have one of those, then call back into the graph and update it for something else. So we can use it to process, to build algorithms that are triggered by data structures. The sky is the limit on this front, and it's incredibly powerful. So we wanted to scale this. We wanted to take this to the nth degree. So what you see here is a plot from our team who set out to take a customer's use case and implement it at 1 million events per second. So instead of this complaint where graph databases have always been slow, let's bring this into the modern world of high volume data processing at scale, and let's test it for resilience. So all these little triangles that you see popping up along the way are different events where we were introducing failure into a running graph to kill machines, to sever the network connections, just introduce the typical kinds of failure that would occur in a live production environment. And the takeaway from all of this is Quine remains resilient, keeps processing. You can follow that green line up and down as it adjusts to the circumstances, because Quine is a back-pressured graph. It means no matter what happens under heavy load or in the presence of network partitions or system failure, then Quine will slow down to remain stable and continue working, continue processing. So even like at number 7, where we lost the complete connection to the data storage layer, Quine pauses its work, the ingest stream pauses. Once that connection is restored, Quine detects it, continues on with its processing. So overall, this was 1 million events streaming in, so 1 million records per second for the ingest side of things. A standing query looking for about a 4-node pattern in the graph, monitoring that graph so that every time it changes, we detect that and essentially run more queries on top of it. And the net result was about 21,000 events per second that were results to this standing query. So we're monitoring the graph live, we're finding 21,000 results per second, we're streaming those out to the next system, serializing those results and everything. So this was our scaling test, and we kind of stopped there as just a nice round number to say, to demonstrate capabilities. But I want to take a minute and go deeper into Quine. How is this even possible? So that was several orders of magnitude beyond what this particular large cybersecurity vendor was able to accomplish otherwise. And so how can we actually do this? Let's dive into some of the details about how Quine works. Under the hood is the familiar graph model. So the subject predicate object connection in language gets represented in a graph with a node edge node style of pattern. So it's universal, it can represent everything that you could talk about. You guys already know this, so this is a knowledge graph conference. You know what the graph model is for. What's novel about Quine though, is that every node under the hood gets backed by an actor. The actor model is a 50-year-old idea from Carl Hewitt in the early 70s, the 1970s. Under the hood, nodes in Quine are backed by what is essentially a single-threaded compute unit. So it's just a logical abstraction to do processing, just a small amount of processing. And actors do all of their work by message passing. So a message gets sent from one actor to another actor, or it comes in from the outside world via message passing. Results get computed, queries computed by sending lots of messages through the actors involved in the nodes for that query. And when those results are ready, message passing to send those messages back out to the outside world. So this is the fundamental architectural choice for how Quine is built and how it achieves a lot of these capabilities. And again, it's really meant for this high volume data processing world. Key for the actor model as well, it is highly distributable. You can take actors and spread them across a cluster and scale out to any degree that you'd like. In order to take one graph and spread it across lots of machines in a cluster, you have to make a choice about how you're going to chop up that graph. And it really comes down to a choice between, do you cut up the nodes and put parts of nodes on different machines, or do you cut the edges? In Quine, we cut the edges. So every node becomes this isolated little island that is connected to other nodes in the graph by half edges. One node stores half of an edge. The node it's connected to stores the other half of an edge. And while doing a query to test whether an edge exists, we relay across that half edge and look for the reciprocal on the other side. If the other side has its reciprocal edge, we've got our full edge, and we can continue knowing that. So this pattern gives us the right atomic unit to then scale endlessly, because we can just hone in and focus on individual nodes. When an edge gets represented as a half edge, then the node can hold its half of the data, and it can treat that almost like a property. And all the concerns from that point on become local to that particular node. Under the hood, focusing on that one node, how does it store data? How does it maintain durability? We use a technique called event sourcing. Instead of storing the data that the node represents, what we actually save on disk is the log of changes, the history of changes to that node. So when you add a property to a node, what actually gets saved on disk is the historical record that at that moment in time, property foo was set to bar. So save that to disk. We can do this in an incredibly efficient manner because we don't have to compare and swap or compare and store values. We can just append the history of the record changes to an append-only log on disk. That can be very fast, very efficient, and highly scalable. So that event sourcing technique lets us look at the data storage layer from this perspective of really just being a key value store. All we really need to store is, for every node in the graph, its value is the history of changes to that node. So different data storage technologies have different trade-offs and work in different ways. Ideally, we want to just go store by appending to the value. Some systems store that directly. In other cases, they don't. We've got simple key value stores. And so a couple different structures of what we store on disk depending on the actual storage technology in order to lean into whatever that particular storage technology is really good at. So that gives us the ability to take something like Cassandra as the data storage layer. This is a robust enterprise quality system that can be scaled endlessly. Teams know how to manage it. It's resilient, it's fault tolerant, it's elastically scalable. And so we can store data in Cassandra and scale without end. So that's a bit about how Quine works under the hood. Let's jump to the next question and ask, how do you use Quine? So there's lots more that we could say. Again, it was 8 years in development for a long time, so lots more to say about how it works under the hood. But how do you actually use it? Well, interacting with Quine is really this process of writing a query. This is the experience we've come to know from graph databases. And so Quine implements the Cypher query language, and we've written our own custom compiler for Cypher to turn this into the kind of distributed instructions, the abstract syntax tree that then we can relay and execute through a distributed graph. So the Cypher language is kind of the interaction model for working with a Quine graph. So with that Cypher language, if we get the rest of the slide, there it is. You can take that query, and as we mentioned before, we're event sourcing, means we're writing to disk the history of changes. And that gives us a certain capability for free. We can have a completely fully versioned graph available in the stream where we can issue a query to get back the answer right now, or we could issue a query plus a timestamp to get back the answer for that query as it was at some historical moment. And we do it by simply just replaying only part of the event log. We've got this log of changes, what happened to a node under the hood, replay that log only up to t equals 4, and you get a certain structure of that node. T equals 7, you'll get the next events that happened, and so on. So you can query not only the present moment in the data stream, but any historical point in the past as well. And if you think about it, that kind of causes a little problem. What if you query before the node actually existed? Oops, yeah, there we go. So this slide. Well, one of the design principles behind Quine is that unlike a typical graph database where it starts empty and gets filled, in Quine, all nodes exist. Every node that you could ever refer to exists. This is a design principle, of course, so it's a mentality for thinking about Quine and how Quine was designed under the hood. When you have a graph of disconnected nodes, it doesn't change the results of any query evaluation because they're disconnected. They don't participate in the query, they're not connected, so we can ignore all these empty nodes, and we can think about all the nodes that could ever exist being in the system before they have an interesting history. And so that lets us simplify some of our operations too. We don't have to create nodes, we don't have to delete nodes. You simply refer to a node and start using it. So this was a design principle at the core of Quine, which kind of required flipping your brain around. And it was really all leading to this. Standing queries are the real novel capability in a Quine graph. A standing query is just a normal cipher query that you issue as a standing query, and from that point on, it stays live and active. As the graph changes, the standing query will propagate itself, it'll push itself through the graph. If it matches, it will continue pushing through the graph. If it doesn't match, it will short circuit and not continue. So that as the data changes, it can update the query results. New results stream out, usually on the order of microseconds from when that data comes in. So regardless of the query size, we can pre-compute most of the parts of putting together a result. We pre-compute most of the query at the ideal moment when it's in memory, when it's most efficient, and then when the last piece of the puzzle streams into the graph, gets connected in to complete the pattern, then we stream that result out right away. So from how to use it, what problems does this solve? So in the industry, graphs have been kind of known as the slow kid. Cool technology, but a little too slow to use in a lot of data pipelines. Let's flip over here. Now, for the first time, graph users get to go on the offensive. So in the data pipeline world, instead of being behind and being the slow kid who can't quite keep up to the fast data processing, we can stream graph results out at millions of events per second. So you can put a graph in your data pipeline. It can sit in between two Kafka topics and do a huge amount of work that would otherwise get spread out and turned into just the huge mess that is involved in microservices. So ideally, we can see what's behind this and see some animated slides here. But the state of the art is microservices that get connected in together to form a graph for data pipelines. You've got a graph implemented across lots of different types of services, connected with edges implemented in Kafka. And in truth, it's hard and it's error prone. It's really expensive. It's brittle. Usually teams build these data pipelines and then 12 months later, they throw them away and build them again because they're so hard to think about and reason about that you can't really maintain it and keep it up to date. But it's kind of the state of the art. Not anymore. Graphs help us solve this problem. So instead of having to spread out across your infrastructure a couple of these key problems about holding on to partial results, hold on to the A's while you wait to connect them to B's, hold on to the B's while you wait to connect them to C's, and hold on to the A-B combinations, hoping that a C is going to arrive in the stream later. Instead of spreading that out across the infrastructure in a data pipeline, or being limited to only however much you can hold in RAM and have to settle for time windows and lost results, putting a graph in your data pipeline actually gives us the ability to get past this old, brittle way of doing things and actually put the connections together in real time while data streams through. No time windows. If the pattern needs to change, you want to look for something different, it's easily updated. Just update the Cypher query and keep streaming. So these capabilities have been really important to the community of users who've started using Quine in just the last year since we open sourced it. Quine was voted the best open source product or project last year in 2022. We're really grateful to the community of folks and the feedback that we get. So if you'd like to try it out, it's at quine.io. I encourage you to check it out. If I were in your shoes, I'd want to see a demo because I wouldn't quite believe it until I saw it. So I want to point you to the tools track tomorrow at 11:30, where there'll be a video showing off Quine. And if you just can't wait, quine.io/demo. You can see it anytime. And with that, I would be happy to answer any questions. If you'd like the slides, you can get them there. And there's links to community stuff as well. Yeah, thank you.
What is the transaction time from when you ingest data into the graph until you see it reflected in one of your analytics?
Great question. It depends a little bit on the scenario and on what you're looking for, but in a lot of cases, standing query pre-computes most of the results. And so it's really just the last item that is ingested that triggers the full and final match. And so that's typically measured as low as single-digit microseconds. Sometimes it's it's in the tens or hundreds of microseconds, but it's typically sub-millisecond.
Have you done any testing in a situation where you have sort of super nodes that have a very, very, very high number of inbound or outbound edges, given the distribution model you talked about?
What a great question. Supernodes have been the bane of graph data forever. Quine has been tested with single nodes in excess of hundreds of millions of edges. Our team is actually currently working on kind of this three-pronged plan to completely eliminate the problem of supernodes. It's not done yet, but it's in process. So the state of the art right now is hundreds of millions of edges, and that's as far as we've tested it.
Just curious, with your history playback, do you ever take a snapshot to how far back does history go? Do you take snapshots so that you don't have to replay the entire history if you have an old query?
Yeah, great question. So the typical pattern for event sourcing is you periodically and kind of heuristically driven roll up the long list of changes into one snapshot so that you can save yourself from replaying the long list and just start from that snapshot. So Quine does that also. And with respect to so snapshots are included in the history replay. And with respect to the long history, we have users who typically use some of the capabilities built into Cassandra for expiring out old history. Sometimes you don't want to keep everything for all time forever. And so you can expire out old history, and this data model is meant to work with that as well.
So how would you, so if I am right now not using or don't see a streaming use case and using AWS Neptune or any of the other providers, but let's say I now have a streaming use case, but still using the base data that's there in AWS Neptune, how would I think about leveraging Quine? So does Neptune still play a role, or everything needs to be in exactly this format?
So great question. I don't know if Neptune supports change data capture or not, but that is okay. So that's one method for kind of getting the kind of a streaming view of data as it's changing coming out of something like Neptune. Whether you still use Neptune or use Quine probably depends on your particular use case. But Quine is meant for what is really this streaming graph search kind of a problem.
So I was somewhat intrigued with the point you're making about writing results back from the output. Is that mostly it sounded like you're talking about mostly metadata characterizing the nature of the data that's coming out, or could you just say a little bit more about the data, the the updates to the graph that you make based on the output?
Yeah. So every time a standing query matches, so there's two parts to a standing query. There's the match side of it. What pattern is it in the graph that is going to trigger some action to occur? That pattern is expressed as a cipher query. It kind of includes whatever you'd like in there. But when that pattern matches, it passes some data results from the match query to the action side of it. That action side can collect results from that query, package them up as JSON or protobuf or whatever, and serialize them and send them out. Or you can do any of a list of things. So the action side of a standing query can issue another cipher query. So to go query something else, fetch other results, or update the graph somewhere else. Maybe both, maybe update and pull together some results and stream them out to the next system. So these actions can be chained together as well.
When you're consuming data, do you consume them from multiple sources? I'm curious, how do you deal with consistency of data coming from multiple sources when you're doing as-of time queries?
Yeah, great question. So imagine several Kafka topics, several sources of data streaming into the same system. The goal is to put them together. And what's hard about this problem is it's going to arrive out of order. So you can't guarantee which thing arrives first, which arrives second. So this is a problem Quine was designed specifically to solve, so that because you don't have to create nodes, you don't have to know which of these things comes first. Take a data model that incorporates both kinds of data, fold them into the same graph, watch for the whole structure, and under the hood, Quine will resolve the standing query in whatever order the data arrives in. So you look for a final pattern. When that final pattern gets there, it doesn't matter if it was A arrived, then B arrived, then C, or C, then B, then A, or B and C, and 2 weeks later A arrives. All of those work just fine. Yeah.
Thank you. So very nice talk. You mentioned being able to do pattern matching. What other graph capabilities are you able to do? Are you limited by cipher? Can you do, for instance, shortest paths between a centrality, tracking communities over time, or other streaming queries?
Yeah, great question. So Quine has a couple graph algorithms built in, like shortest path. It's callable from a cipher query. So you can say, given any two nodes, run a shortest path query. There's plans for extending these and adding plenty of other graph algorithms as well. If anybody here has a favorite you'd like to contribute, you can find the GitHub page, and that would be fantastic. But additionally, Quine is also built with some other kind of correlating things that are meant to walk the graph, for instance, and stream out random walks for the sake of graph embedding or integrating with graph neural networks. I think we're out of time. Thank you very much. If there are other questions we didn't have a chance to get, I'll be around. Please find me afterwards. Thank you very much for your time and attention.